All right, so today we're going to talk about functions and logarithms. We're skipping section 1.4 because it's parametric, which is a BC calculus topic, and we're not going to cover it today or this year for AB Calc. So one-to-one function, we know a function in general has one y value for every x value. So, and remember that means it passes the vertical line test. Now, a one-to-one function not only has one y value for every x value, it has only one x value for every y value. So in a function, you can never repeat x values, but you could repeat y values. For instance, down here at the bottom on this absolute value graph, it's a function because it passes the vertical line test, but it has two places where the function crosses this y value, whatever that happens to be. It's so teeny I can't read it. But it has two y values. The y values can repeat. Now the x value can't. I only use this x value once and this x value once. But, however, if we're talking one-to-one, not only can your x values not repeat, no y values repeat as well. But also x values because that makes it a function. All right, so to test for one-to-one, you actually use the horizontal line test. Now, it has to pass the vertical line test too, okay? Because that makes it a function. But to be a one-to-one function, it has to pass both. So, like this very first one, it is not one-to-one because it hits in three places. Now, there may be places it hits only one, but if there's any one line you can draw horizontally that crosses, it is not one-to-one. Now, it does pass the vertical line test. It is a function, but it's not one-to-one because it does not pass the horizontal line test. Now, this next one, it is a function. There's nowhere I could draw a vertical line that hits more than once, and there's nowhere I can draw a horizontal line. So this one is, in fact, a one-to-one function. The next one, it is a function. Even remember in this spot, it is a function. It is not hitting twice because though that bottom one is a closed point, that's an open point, so it's not actually a point on the function. So that's good. It is a function. It is not one-to-one, though, because every time I draw these horizontal lines that intersect these segments, it hits infinite number of points. So that is not one-to-one. Now, this last one, it is a function. It passes the vertical line test. It is not one-to-one because it is, in fact, hitting in two spots. There is a spot here, whoops, down at the bottom where it hits the vertex that it only hits once, but there are many lines where it hits twice. So it is not one-to-one. It is a function, but not one-to-one. All right, so determine whether each of these equations is one-to-one. I'm going to use a graph for my purposes right now. So remember, the parent function for this looks like a sideways parabola. That is a function, and it does look to be one-to-one. So yes, this is a function, and it is one-to-one. I should write it is a one-to-one function in my instructions. It would have to be a function to be one-to-one, but we'll be picky. Okay, this next one, however, because it's y squared rather equals x, think about what it would look like if it was y equals x squared. That would be a whole parabola this way. If it's x equals y squared, it's a whole parabola, but sideways. Okay, so instead of just being a half a parabola like this one, it's a whole parabola. So this one is not a function, so it's not one-to-one. Okay, now, this last one is an absolute value problem, which we kind of talked about on the last page, or it was very similar. And so, yes, it's a function. Okay, but nope, it's not one-to-one because it doesn't pass the horizontal line test. So, no. All right. Now, algebraic definition of inverse. Now, first of all, just so you remember, an inverse function has a notation with that little -1 in the corner, it does not mean 1 over like it does as an exponent. It's not an exponent. It just means f inverse of x. You say, or the inverse of x. Now, algebraically, you define functions as inverses. F and g are inverses. If f of g of x equals g of f of x equals x. I should actually say if and only if. If you guys remember from geometry, some of you, if you put two IFFs, if and only if, that means that it can work backwards. We'll talk more about that later. So let's check if these two functions, f and g at the bottom, are in fact inverses. So how you prove that is you have to do both f of g of x and g of f of x. So we're going to do the first one, f of g of x first. How the heck do you do that? So I know what g of x is. I'm actually just going to rewrite it by substituting g of x in here. So g of x is that. I'm just changing the g of x into the equation for g of x. Just straight up substituting. All right, so now I'm only going to do things to the right side of the equation. Now, saying f of the cube root of x means substitute this guy in anywhere you see x in f of x function. So I'm going to take that f of x right here and I'm going to change that x. Okay, I'm going to leave everything the same except I'm going to change the x part to the cube root of x. So I have the cube root of x to the third then because I have to change just this part to the cube root of x. All right, now, what's a cube root cubed? Well, they undo each other. So all I'm left with is just x. So there's that. So half of it has worked out. We've got f of g of x equaling x. We also have to prove that g of f of x also equals x. So let's figure that out. All right, so g of f of x, I'm going to substitute just the f of x part in because I know exactly what that is. F of x, I'm just changing that to what it says f of x is. F of x is x cubed. Okay, straight up substituting. Now, this also means substitute. It means in g, anywhere you see an x, change that to an x cubed. Okay, so inside of my x, I'm just going to change that, and it's in my cube root rather, I'm going to change that x to an x squared, cubed, x cubed. Whew. All right, so I'm going to move this up a little bit. So if I look at this, the cube and the cube root cancel each other out, so I just get x. So in fact, f of g of x, it equaled x. G of f of x equals x. So, yep, it's a function. Excuse me. They're inverses. All right, now, how about this next one? It's not called f of g of x and g of f of x, so we're going to just call them g of x and f of x. All right, so we're going to check this out. So f of g of x, we'd have to see if that equals, oops, I missed a parentheses, if that equals x. So I'm just going to straight up substitute. I'm going to change my g of x into e to the x. All right, so now I'm going to take my f and substitute e to the x in. So I called this one f this time. So I'm going to substitute, here's my f of x, and I'm going to change that x into an e to the x because it says substitute in e to the x instead. Well, if you remember your log rules, natural log is really log base e, so a log of an exponential, they undo each other, just x. So yep, in fact, that is true. We're going to go over the log rules in a second if you don't remember them. All right, so g of f of x. We've got to check that and make sure it is also x. So we're going to leave the g and we're just going to straight up substitute what f of x is. F of x is natural log of x. So just substitute that in. All right, now this says take g And wherever you see x, change it to ln x, or natural log x. So I took g, which is e to the x, and I changed that x to a natural log x. Well, again, our log rules say e and natural log cancel each other out, so back to x. So, yep, these are also inverses, because both g of f of x and f of g of x equals x. Now, if we want to actually find an inverse for a function, we actually have to do these steps. Switch x and y, and then solve for y. Make it back to a function form, basically. So it says show that f is 1 to 1 and find the inverse. So we have two things to do here. So show it's 1 to 1. First of all, it's a line. We can look at it. And it looks like up 4 and then has a -2 slope. So it looks something like this. Okay, I did the -2 in my head there. All right, so I've sketched. So pretty sure it's a function. It passes the vertical line test. I'm pretty sure it's 1 to 1 because it passes the horizontal line test as well. Okay, so we got that. Now, what about the inverse thing? So let's remember how to do that. To do that, we need to go ahead and switch x and y. Remember, this is really y. I'm going to cross it out for a second. Switch the x and the y. And then we need to solve it back for y. So x, I'm going to subtract the 4 from both sides. And I'm going to divide by -2. Now, you can leave it like this. All right? Or you can go ahead and distribute. Just remember, division is really multiplying by the reciprocal. So if you divide, it distributes just like multiplication does. So that would be the same thing. That is the inverse of f. So I'm going to use the notation for inverse and say that's the inverse of f. All right. Now, graphical definition of inverse is that they're reflections over the line y equals x. So if they are inverses, if two functions are an inverse, the reflections of each other over the line. Over the line y equals x. All right. So I drew in that line y equals x right there. Okay, so if this is the function g, okay, a function g of x, g inverse would be this guy right here. It's a reflection. It's like a mirror line. This reflects here. This guy reflects here. Any point right on y equals x is its own reflection, and these guys reflect. Okay, so point by point, we can draw that. So since we have this guy right here, okay, if this is the function, we'll call it h of x. If we have to draw an inverse, so if this one right here is at 1, 0, our inverse, switch x and y, 0, 1. And let's see if I choose this point just because I want to have one more point to kind of get my bearings. This is 3, I don't know, maybe 1.5-ish. We're going to need to go to 1.5-ish, 3. Switch x and y. You can switch every single point, just switch x and y. X and y are still switched. And that's what happens. It ends up looking like a reflection, if you can trust my very poor drawing. Okay, so logarithms. Logarithms are inverses of exponentials. So y equals log base a of x is the inverse of y equals a to the x. Logarithms and exponentials are opposites. So a to the log base a, x, e to the natural log of x, x. We kind of talked about that, used it in our last one. Don't forget some of our log properties, that when you multiply inside of a log, you can, sometimes it's considered more simple to do it like this. Sometimes it's considered more simple to do it the other way. It depends on what math you're doing. That's an A right here. Sorry, it doesn't look so good. All right, so really it's like 2 logs added. Conversely, if you're dividing, it makes it be opposite. So you would be subtracting 2 logs. So sometimes if you have 2 logs apart, it's nice to condense it into 1 log. And sometimes it's nice if you have 2 logs together to take it apart and make it two big logs. All right, now don't forget if you have an exponent on a log, you can bring that down in front. Okay, so you can bring that down in front. We use that a little bit for the last section. Don't forget your change of base rule is you can do log of any base, x over a log of any base, a, but we use the common log. Remember, these are the common log, and it's in base 10. It's automatically assumed if they don't tell us. And this one's the natural log. And its base is e. Okay? So you could also do natural log of x over natural log of a. Those are the ones we usually use because they're on our calculators. But actually, our new calculators will do any base, so you don't need to do change of base. But you may need it, especially for those of you taking the AP exam. All right, so how do you solve some log problems? So these are going to be review, but, you know, just to remember our log rules. Okay, so there's two ways if I need to solve for x. Now, this one has a t in it also, so we're going to have our answer will have variables in it. That's all right. But if I want to solve for x, and I have a logarithmic equation, you can kind of think of doing it one of two ways. You can switch this logarithm into exponential form, or you can do what's called exponentiate both sides. That's e, and then I'm making the function the power. So, for example, if I had 2 to the x equals 2 to the 5, I hope you would tell me, well, those exponents have to be the same. So if I already knew these original things were the same, let me erase it out. If I knew those two original things were equal, if I make them be exponents, they still have to be equal because they have the same base, so those exponents have to be equal. All right, but that's nice then because this e and the ln cancel out because they're inverses. Okay, so then I get x equals e to the 3t plus 5, and that's what x equals. Life is good. It's all done. All right, now this other one over here is an exponential. If you have to undo an exponential, the opposite is a log. So to get rid of an e, you'd use natural log. Okay, so if I natural log one side, I have to squeeze it in on the other. Okay, so I end up with, let me rewrite it so it looks a little better. I end up with that equation if I take the natural log of both sides. Now remember, an exponent can come down in front, so I'm going to rewrite it. Okay, but one of our fancy schmancy log rules is natural log of e. It cancels because natural log and e undo each other. They're inverses. So I end up with 2x equals natural log of 10, which means x equals natural log of 10 over 2. If you're really excited about going into your calculator and figuring out what that is, go for it. All right, you can do that, but that's an exact answer. I like it. I'm done. You cannot divide the 10 and the 2 because the 2 is not a natural log and the 10 is in the natural log. Can't do it. Don't do it. Don't be tempted. All right, so now I guess I want to do a little extra example about that. So I'm going to come back to it in a second. Let's do this next example. Sarah, which is spelled wrong, sorry. Sarah invests $1,000 in an account that earns 5.25% annually. Okay, it's compounded annually. So how long will it take the account to reach $2,500? All right, so remember our formula that we learned in the last section. Now, I'm not putting the n in because, okay, so technically there's a divide by n. I'll put the n in. The n is 1, though, because it's compounded one time annually. So it's compounded once. So I leave the n out when it's annual. But then I need, let's see, she's investing $10,000, or excuse me, $1,000. So that's our principal. Our rate is 0.0525. I'm not going to write the 1. Okay, I'm not going to write the divide by 1, and I'm not going to write the t, or excuse me, the 1 before the t. I am going to write the t. We don't know how much it is, so that is how long. That's asking what's t. And my, it wants our account to reach an amount, or the A, of $2,500. So there we go. That's what we have to solve. So how do we do that? Well, first things first, divide both sides by 1,000. All right, so if I do that, if I divide both sides by 1,000, I end up with 5 over 2. If you want to write 2.5, all the power to you. Okay, equals 1 plus 0.50525, which you could write as 1.0525 to the t. Now, I need to get the exponent down. If I have an exponential and I need to solve for the exponent, I need to take a log. The opposites of exponentials are logs. Now, I find it easier. You can use any base you like, but I find it easiest to just use natural log or common log. I know you're probably used to using the common log, but they use a lot more of natural log in calculus. So I'm going to try doing natural log just to get you used to it a little bit more. So you do natural log of both sides, and that means that t can come down in front. So I'm about to give up on this 5 over 2. I might change it to a decimal. The t comes down in front because it's an exponent, and natural log then, I'm going to put a times sign here, and then it's 1.0525. I'm going to put that together. All right, so to get the t by itself now, I have to divide this guy out. So I'm going to divide both sides by that. It's just a number, which you can put in your calculator. So I'm going to divide both sides by that crazy decimal. And then I get natural log of 2.5, finally bailed on it, over natural log of 1.0525. This is a calculator problem. Go for it, get an answer. That should be 17.90 years. Okay, so that's how long it would take to get that far. All right, now, I don't want you to make the mistake of our log rules. We said that if we have natural log of y, x divided by y, I can split that up into 2 logs subtracted. This is not the same thing. This is not 1 natural log of 2 things divided. Okay, of 2 things divided. It's 2 logs divided. That's totally different. Don't use that rule on it. It doesn't work. It's just a little caution. I noticed people doing that. Now, well, how do I graph f of x if I'm graphing a logarithm? Now, we probably know parent functions, but let's talk about it again just to, see exactly how you do it. Now, this is what it would look like. I'm just changing the f of x to a y. Now, I find it easier to graph these and conceptually understand it if I go ahead and switch this into the exponential form. You can think about it as exponentiating both sides by making 2 the base and changing the equation into exponents, which is totally allowed because the exponents have to be the same for this equation to work. But then these guys cancel, so you have 2y equals x. That is a little easier for me to conceptualize, so I'm going to actually go ahead and put some values in for y because I can do that. Okay, so if I put in 0, I'm going to get 1. So if I put in 0 for y, I get anything to the 0 power is 1. If I put in 1 for y, I'm going to get 2. If I put in 2 for y, I'm going to get 4. If I put in 3 for y, I'm going to get 8. On the other side, if I put negative 1 in for y, I'm going to get 1 over 2. If I put negative 2 in for y, I'm going to get 1 over 4, and so on. So I can graph those points and get a graph. Let's see. I'm going to graph them. I'm going to stop it so it's going to jump all of a sudden. Okay, so I've got my points. I'm going to go ahead and draw this. Now, it is coming to an asymptote here at the y-axis, which, if you think about it, you can never have the x value end up to be negative. Like, even though we're putting in a negative exponent, it just makes that a fraction. Okay, so it's going to be more and more decimally, but it'll never end up being That's a technical term, decimally. It'll never end up being negative. Won't happen. So this is an asymptote right there, and there you have the graph. And how I did that was I used the inverse idea to take care of it. It is also the inverse function of 2 to the x equals y. If I graphed that guy, you would see it was an inverse. Let me do that. And there she is. Okay, and if I did the y equals x, you could see that they are, in fact, reflections of each other. And here, even the asymptotes are reflections of each other. And there you go. All right, then that's it today.